DSPy's refine module implements an iterative improvement mechanism with automatic feedback loops, extending basic prediction refinement by incorporating self-correction through generated feedback. This pattern enables adaptive optimization where each unsuccessful attempt informs subsequent iterations, creating a closed-loop enhancement system. We're about to examine how this refinement process is configured, focusing on the initialization parameters that control iteration behavior, reward evaluation, and error handling thresholds. The setup will reveal how the module balances persistence with early termination while maintaining quality constraints.
Hash stop after the first error. Refine equals DSPy. Refine. Module equals ka. N equals 3. Reward fn equals one-word answer. Threshold equals 1, 0. Fail count equals 1.
This code demonstrates the refine module's error handling configuration, specifically setting it to stop after the first failure. The refine module extends best of n by adding automatic feedback loops between attempts, where each unsuccessful run generates feedback that's used as hints for subsequent iterations. The configuration shows fail count equals 1, meaning the refinement process will terminate immediately if any attempt fails, rather than continuing through all n equals 3 iterations. This is particularly useful when you want to fail fast rather than waste resources on likely futile subsequent attempts. The threshold equals 1, 0, indicates only perfect scores from the reward fn will be accepted, with one-word answer serving as the strict evaluation criterion. This approach trades resilience for efficiency, as it prevents the system from attempting all iterations when early failures suggest the task parameters might be fundamentally problematic. It's a practical choice when you have confidence in your reward function's ability to detect unrecoverable failures early, or when computational resources are constrained. The feedback mechanism remains active for non-failing attempts, allowing the system to potentially improve between the first and second attempts before any failure occurs. Let's break it down.
Refine equals DSPy. Refine.
Creates a refine instance using DSPy's refine class, which implements an iterative improvement mechanism with automatic feedback generation between attempts. The line initializes this refinement process, but doesn't show any configuration parameters or the specific module being refined.
Module equals ka.
Assigns the string value ka to a variable named module. This creates a simple identifier that likely categorizes or specifies a module type, with ka suggesting a question-answering context. The variable can be referenced later to determine module behavior or configuration.
N equals 3.
Assigns the integer value 3 to a variable named n.
Reward fn equals one-word answer.
Assigns one-word answer as the reward function for evaluating responses, which will be used to score and select outputs based on whether they are single-word answers.
Threshold equals 1, 0.
Sets a threshold value of 1 for the refine module's feedback mechanism, determining the minimum performance score required before feedback is generated and used for subsequent attempts.
Fail count equals 1.
Initializes a counter variable named fail count with the integer value 1. This variable will track the number of failed attempts, starting from 1 rather than the typical 0, suggesting it may be used in a context where counting begins after the first failure. The refine module's configuration demonstrates a deliberate trade-off between resilience and efficiency in iterative improvement. By setting fail count equals 1, the system prioritizes early termination over exhaustive attempts, immediately halting refinement if any iteration fails. This pairs with n equals 3 to create a bounded process that won't waste resources on likely futile subsequent runs when early failures suggest fundamental issues. The strict threshold equals 1, 0 enforces perfection through the one-word answer reward function, ensuring only flawless outputs pass while still allowing the feedback loop to potentially improve non-failing attempts. The module's automatic feedback generation between iterations remains active for successful runs, enabling incremental improvement when the task parameters are viable. This setup is particularly effective when you have high confidence in your reward function's ability to detect unrecoverable failures early or when operating under computational constraints. The combination of these parameters creates a fail-fast system that maintains quality standards while optimizing resource usage.
The refine that trips on its own threshold learns.